Okay, so I guess we are ready to start. So hello everyone and welcome to the next season of the Extreme and Probabilistic Combinatorics webinar. So after a little bit prolonged summer break, we are again online and streaming. Anyway, so our first speaker is Tash Morrison from University of Victoria, and she's going to talk about some uncommon systems of equations. So I guess, Tash, the stage is yours. So,
well, thank you very much for the invitation. It's very nice to be here. It's very nice to be able to give or watch seminars with all these people in all these different places. And this is something I guess I hope will continue even once everything gets more normal. So what I'm going to talk about today is some work that I've done joint with Nina Kamchev and Anita Liebenau about uncommon systems of equations. So I'll start out by talking about kind of the notions of commonness and uncommonness in graphs, and then we'll talk about what it means in the equation setting. So I imagine many of you are very familiar with these things in the kind of graph setting. So I'm just trying to change my slide and it's not moving. Here we go. Okay, so there's a very, very famous theorem of Goodman, I'm sure many of you are familiar with, which says that the density of monochromatic triangles in any two coloring of the edges of the complete graph Kn is always asymptotically at least 1/4. So when n is very, very big, count the number of red triangles, count the number of blue triangles, divide by the number of triangles, and this is always going to be at least 1/4. So it's not possible to come up with some coloring which has very, very few monochromatic triangles. One way of thinking about this result is thinking, well, what does it say? It kind of says that a random two coloring minimizes the number of monochromatic triangles, because if you imagine coloring your edges red and blue independently, probability 1/2, the expected number of monochromatic triangles is going to be 1/4. It is the case that there are other colorings that will also have very few monochromatic triangles. So for example, imagine a complete bipartite graph where within the classes you color all red and across you color blue. Well, this also has the density of monochromatic triangles equal to 1/4. It doesn't look random like at all, but the point is really that however you color this graph, you're not going to have fewer than density 1/4. So this was a very, very nice theorem. So Erdős in 1962 conjectured that this wasn't just true for triangles, but was true for any complete graph. So Erdős conjectured that if you wanted to minimize the density of monochromatic copies of a complete graph KT, well, you're never going to be able to do better than just by taking a random coloring. So the density expected in a random two coloring is going to be the smallest density you can ever achieve. So I guess you can think of this as saying, as you conjectured, that random is best for minimizing. And a little while later, after this conjecture, Bern-Roster made a bolder conjecture, which said, well, not just do we think that the density of monochromatic copies of a clique on T vertices is minimized by a random two coloring. Well, in fact, for any graph H, they conjectured that you couldn't do better than the density expected in a random two coloring. So I guess two very nice conjectures. Unfortunately, both of them are false. But before we talk about that, let's talk about definition. So I'm sure many of you are familiar with this definition. So you can say that a graph is common if the density of monochromatic copies of the graph is asymptotically minimized by a random coloring, otherwise it's uncommon. So what do these conjectures say? Well, Erdős conjectured that KT is common, and Burr and Roster conjectured that every graph is common. But I guess, so when the conjectures were, I guess, in the Burr-Roster conjecture was in the 1980s, so almost 10 years later, Andrew Thomason and Sidorenko independently came up with graphs which showed that these conjectures were false. So Thomason showed that K4 was uncommon, and Sidorenko showed that a triangle with a pendant edge is uncommon. So even though, and so to notice that the counterexample of Thomason disproves both the conjecture of Erdős and the Burr-Roster conjecture, and the counterexample of Sidorenko disproves the Burr-Roster conjecture. So despite the fact that these conjectures were very false, since then, there's been some work determining which graphs are common and or uncommon. So for example, some graphs that are known to be common are trees and cycles and even wheels. And there's a very nice result from 1996 by Jagger, Stovacek, and Thomason, which they proved that any graph containing K4 is uncommon. So any graph H where it has K4 as a subgraph, this graph will be uncommon. So this gives a really, I guess, a large, interesting family of graphs that are uncommon. Okay, so just very briefly, I don't intend to talk about this for very long, but it would probably be silly of me to talk about commonness and uncommonness without briefly mentioning the very, very related property of being Sidorenko. So you can say that a graph is Sidorenko if the density of copies in a graph with fixed edge density is asymptotically minimized by a random graph of the same edge density. So if you haven't seen this before, don't worry too much about this. I'm not going to talk much more about it, other than to say that there's a very famous conjecture, which is Sidorenko's conjecture, which says that all bipartite graphs are Sidorenko. You might want to think for a second about if you consider a graph with an odd cycle, well, it's possible to make graphs which just don't have any copies of this, right? So it doesn't make any sense to ask about minimizing the density of a graph with an odd cycle, because you can just get rid of this. But the relation to what I'm talking about is that if H is Sidorenko, well, it automatically implies that it's common. So a lot of the time when people have proved that graphs are common, actually what they did was they proved that they were Sidorenko. And similarly, when we talk about systems of equations, so we've got various results which talk about uncommon systems of equations. We've also got some results, which I'm not going to talk so much about today, which show that things are common. In fact, what we did show, we showed that they were Sidorenko. But let's talk about uncommonness today. So hopefully you're all fairly familiar with the graph setting. Let me tell you what I mean by Sidorenko and uncommon systems of equations. So what about equations? So just for example, we're going to be thinking about kind of equations that look a bit like this. So what's the rough setup that we're going to be thinking of? So to start with, just imagine a single equation. So we've got k variables, which are x1 up to xk, and we can just call this L of x, this form here. And our coefficients ai, you can think of them as being, I don't know, either non-zero members of your favorite abelian group or just non-zero integers. Now, once we've got this set up, we can define the solution set of the equation to be the k-tuples. So imagine you've picked your coefficients inside this group. It's just the k-tuples in this group that solve the equation. So for example, if we were considering this equation, x minus 2y plus z is equal to 0 over the integers, then what are the solutions? well, this is just a 3-term arithmetic progression, and the solutions are all tuples of the form a plus d, and a plus 2d, where a and d are integers. So you can see this, right, if you just substitute x for a, y for a plus d, z for a plus 2d, this solves this equation. And just for example, right, 1, 2, 3 is a solution, 7, 12, 17 is a solution. Hopefully, so this notation kind of sol L is clear. Okay, so more specifically, what are we going to be interested in? Well, we're going to be interested in solutions inside particular subsets of our kind of world we're living in. So for a fixed, say, subset of integers, or a fixed subset of this group G, we're going to define sol LA to be the k tuples which solve the equation, but which lie in this set A. This fairly natural extension of this notation. And very broadly speaking, the kinds of questions we're going to be thinking about is what can we say about the size of this set? So given our system or our equation L, and given our set A, what can we say about the number of solutions to L inside A? Or relatedly, what can we say about the number in A plus the number in A complement? So how should we think of this? Well, imagine coloring the members of your group red and blue, and the red ones are your set A and the blue ones are your set A complement. Well, this second question here essentially says, what can be said about the number of monochromatic solutions to your system? So there are actually many, many questions in additive combinatorics kind of can be phrased in terms of asking about sol LA or sol LA plus sol LA complement for various systems or various sets. So for example, the very famous van der Waals theorem, which says, I'm sure, again, many of you are familiar with this, but if you're not, you should definitely go and look at the proof because it's pretty cool. So if k is an integer, then basically it says then there exists some n0, which depends on k. So once you've got this n0, so you've got any coloring of some long enough sequence of integers, you're going to find a k-term arithmetic progression in there. So, you know, you imagine you color the first n0 integers red and blue. However you color this, you're going to find a sequence of either k red or k blue. And I've written this, I've said here any two coloring, but actually this is true. You could say there's an n0 which depends on k and r, and this is also true for an r coloring. So here's a little picture to demonstrate what I mean. So what is a k-term arithmetic progression? Well, it's just a generalization. So these first three terms here were an arithmetic progression. K-term arithmetic progression is just the same thing, but for k terms. And so I've done a tiny example here. I've taken the numbers 1 up to 9, and I've colored them red and blue. And I think you'll observe that whether I color 9 red or whether I color it blue, we're going to get a 3-term monochromatic arithmetic progression. So I think we can get 3, 6, 9 if we color it red, and if we color it blue, I think 1, 5, 9. And I appreciate this is nowhere near a proof, and it's just one example. But I think if you play around with this, I'm not sure you're going to be able to color these numbers in a way that you will avoid a 3-term monochromatic arithmetic progression. So I guess talking back to the language of our previous slide, this theorem can be stated in a way which says that, in fact, the number of solutions to a KAP in a set A plus the number of solutions in a complement is always at least 1 for any subset when n is big enough, essentially, right? So this is a theorem which is talking about the number of monochromatic solutions to this system. Very briefly, that just, again, there are many, I guess, areas of additive combinatorics which talk about the number of solutions. So for example, Roths Theorem, which is a very famous theorem, which is, again, I guess, talks about arithmetic progressions, 3-term APs, says if we have a set with no 3AP, then it has to be small relative to the size of 1 up to n. The best known bounds on this are given by Bloom and Sisask, and Semerades theorem, which can be thought of as a generalization of Roths theorem, essentially says the same thing, but for k-term arithmetic progressions. This was just a brief detour into additive combinatorics. Let's now talk more specifically about the problems we're going to talk about today. So as I said, we've got the setup, we've got this equation, Lx, and for the rest of the talk, we're going to think about our coefficients inside Fq, where you can think of Q as being prime power. So take your favorite finite field, and just, it's sometimes helpful to have this notation, sol little La, because there's not so much space on the slide. And if I want to write lots of lines, it's just going to mean the same thing. Okay, so finally, I'm going to tell you what it means for an equation to be common. So we say that an equation L is common over Fq if the density of monochromatic solutions in any two coloring is asymptotically at least what you expect in a random two coloring. And we say in a two coloring of Fq to the n as n tends to infinity. So it might be the case that you have these very small second order terms, but when you sort of asymptotically, the main order term is going to always be the expected density in a random two coloring. So how should you think of this? Well, just imagine your Fq to the n, and imagine, right, the red solutions and the blue solutions, and you say, okay, my system's common if the number of the monochromatic solutions here is at least what you expect when you color these things randomly. Now, that definition is it's very nice. It's not so convenient to work with. What's very convenient is to have something that's you can grab and it's more numerical. So actually, it's the case if you do some calculations that we can say that any sensible system is common over Fq if any subset of Fq to the n, well, the number of solutions, I guess the number of red solutions plus the number of blue solutions is at least 2 to the 1 minus k over sol L Fq to the n. What do I mean by sensible system? I just mean that there are a few silly things that don't happen. We're not getting rid of any interesting systems here. It's just helpful to be able to have a reasonable thing to write down as a thing. But we want to show that it's common. We show that this holds. We want to show that it's uncommon. We can find a set where the number of solutions is less than this thing on the right-hand side. So there's a very nice paper of Saad and Wolf, who initiated, I guess, the study of systems of equations and asked about which equations and systems of equations are common or uncommon. And they also asked analogous questions for the Sidorenko property. So let's just do a little example to start with. So let's take our favorite single equation, which is the three-term arithmetic progression. So let's say we've got, it's z1 minus 2z2 plus z3 is equal to 0. And let's take some subset of Fq to the n, and let's consider the number of solutions in A plus the number of solutions in A complement. So first thing to observe is that you can parameterize the solutions of the three-term arithmetic progression in this way. So what we can do is we can actually write down exactly what this number is here using indicator functions. So if we take the sum over all xy, well, what does this term say? Well, this term basically gives us a 1 whenever each of these three things are in our set. And this term here gives us a 1 whenever each of these things is in our set A complement. So if we sum over all x and y, essentially what it's going to do, it's going to pick out exactly the number of red solutions and the number of blue solutions. So what we can do now, right, we want to divide through because we sort of care about the density. That's sort of such an interesting step. But if we use the fact that this indicator function of a complement is 1 minus the indicator function of a, well, what we obtain is, so basically, I'm not going to put the whole calculation on the slide. I know it's very, very difficult to follow calculations on a slide, but basically just using this simple substitution in your equation, multiplying out these factors and rearranging terms, you get a lot of cancellation. And what comes out is exactly this, which you can see can be rearranged to this. So just observe before I go to the next slide. So we've said that the density of the monochromatic solutions here in a particular set A is exactly equal to this. Now, in particular, it means, right, then it's at least this. And this is what you'd expect in a random set of density A. So this says that 3-term arithmetic progressions are common. In fact, this whole argument works exactly the same way for any single equation in an odd number of variables. You can do the same thing and you can pull out exactly, it's kind of nice, you can pull out exactly what this number is. So this was an argument of Cameron, Cilleruelo, and Serra. So they said, okay, in general, right, if you're considering a single equation, and k is odd and your coefficients are in your field FQ, but not 0, then this is common whenever k is odd. So that's very, very well understood. And the next question is, well, what about when k is even? So Saad and Wolf proved that now if we have an equation with a similar setup, they proved that it's common whenever the coefficients can be partitioned into pairs which sum to 0. If you do that, you can do, I think, a kind of Cauchy-Schwarz sort of argument, which shows that this is always going to be common. They made the conjecture that this is common if and only if the coefficients can be partitioned into pairs which sum to 0. Okay, so a little while after this, their conjecture was actually proved by Fox, Pham, and Zhao. So actually, single equation systems are now very, very well understood. And so let me summarize what we understand about single equation systems. So I've written a theorem of these 3 sets of authors. That's because they all proved a different part of this theorem. If you put their work all together, you get a full characterization of single systems. So if we've got this equation here, Lx is a1x1 plus a2x2 plus so on, we know that firstly, it's common whenever k is odd. And then the second part of the theorem concerns when k is even. And it says, well, if k is even, then it's common if and only if the coefficients can be partitioned into pairs that sum to 0. So for example, an additive quadruple, which is an equation x plus y equals z plus w. If you take this all onto one side, right, what are your coefficients? It's 1, 1, minus 1, minus 1. And these can be paired up. So you can take the 1 and the minus 1, you can take the 1 and the minus 1. So they're partitioned to pairs which sum to 0. So in fact, it's common. So are there any questions about this single equation case? We're all happy. Okay, so single equations are very, very well understood. But one thing that these sets of authors also addressed in their papers was, what about not just single equations, but systems of equations? So I guess this was kind of initiated by Saad and Wolf, and Fox, Pham, and Zhao also asked the question, well, what can you say about systems of linear equations? Which systems of linear equations are common? So what's the kind of setup here? Well, it's kind of like just the single equation, but we've now got more than one equation. So for example, 4-term arithmetic progression, which is the one we're going to think about a lot today. This is just the system of equations where we have 2 equations now. Again, right, you could imagine you could have as many equations as you want. Your coefficients are all in some predefined group or field or whatever. So the 4-term arithmetic progression, each individual equation is a 3-term arithmetic progression. And you can see that, so we've got 4 variables, and the solutions to this pair of equations now is this tuple a plus d, a plus 2d, a plus 3d. That's why it's called a 4-term arithmetic progression. So 4-term arithmetic progressions have actually been very, very well studied. So Julia Wolf in 2010 proved that our 4-term arithmetic progressions were uncommon over ZP. So she constructed a set such that the density of the monochromatic arithmetic progressions in this set is very small. Tim Gowers found a random-like construction of density 1/2, which had few monochromatic 4-term arithmetic progressions. So when I say random-like, I mean that the Fourier coefficients of the characteristic function of this set are small. I guess because the construction of Julia Wolf was very, very structured, and it was an interesting question to say, does there exist a random-like counterexample? So both of these ideas or ideas that the kind of constructions, they very much use the geometric structure of 4-term arithmetic progressions, and kind of how, right, the 4-term arithmetic progression is a really nice kind of set, right? You've got these 4 points and they're kind of equally spaced around. And so they ask the question, well, is it true that any system containing a 4-term arithmetic progression is uncommon? So for example, Saad and Wolf proved in their paper that it is uncommon. Any system, they proved that a 4-term arithmetic progression itself is uncommon over F5. And they showed an extension of their proof, which showed that in fact, a 5-term arithmetic progression is uncommon, again, over F5. So they said, well, is it the case that actually any system containing a 4-term arithmetic progression is uncommon? So you can think of this question as being an analog of this theorem of Jagostovicek and Thomason. Right, they proved, as we said, when we were talking about graphs, they proved that any graph H that contains a K4 is uncommon. Right, this is a similar kind of thing. It's can you say that any system containing a 4-term arithmetic progression is uncommon? And so before we kind of talk about this question, let's just check we know what we mean by, what does it mean to contain a 4-term arithmetic progression? To get our heads around this question. So when we say any system, well, we just mean a system of linear homogeneous equations. What do we mean by containing a 4-term arithmetic progression? Well, here is our favorite set of equations now, our 4-term arithmetic progression. So we can write it like this, but you can also observe that there are many, many different ways you can write this 4-term arithmetic progression, right? Any multiple of one of these equations, if you add it to the other, right, the solutions are still going to be the 4-term arithmetic progression. This is, right, it's linear algebra. So there are many, many, many different ways to write this pair of equations. So by containing a 4-term arithmetic progression, it doesn't really make sense to say, oh, when I look at my system of equations, I get these 2 specific equations there, right? Because there are many different ways they could be there. If we had other equations in our system, we'd added multiples to our 4-term arithmetic progression, the whole thing might look very confusing. So the best way to think about kind of a system containing a system is to think about the parameterization of the solutions. So you can think about a system containing a 4-term arithmetic progression if when you look at the solution set, you end up with these four, you can parameterize the solutions in such a way that you end up with an A plus D, A plus 2D, and A plus 3D. And these stars could be anything, right? They could be things in terms of A and D, or they could be things in terms of many, many other variables. So this is, roughly speaking, what it means to contain a 4-term arithmetic progression. And our theorem that we proved, it says, well, if Q is a prime power, and we have a system which we, right, as before I said, we're only going to talk about sensible systems. I'm not brushing anything under the carpet here. I'm just taking away silly things that make a system trivially common. So if we have a sensible system over FQ, we proved that if the system contains a 4-term arithmetic progression, then it is uncommon. So for example, a 5-term arithmetic progression, which you can imagine, right, we've got these two 4-term arithmetic progressions and another equation, well, that's uncommon. And so actually what we proved is a much more general theorem. So going back to, let me just use some terrible notation now. So let's call a 4-term arithmetic progression and well, let's call a system containing a 4-term arithmetic progression an A plus D, A plus 2D, A plus 3D system. So if we do that, we can rewrite our theorem in this way. I'm not really saying anything new yet, but our much more general version of our theorem says, in fact, if we have a sensible system that contains an xy, ax plus by, cx plus dy system, where A, B, and C and D have these very, very weak constraints on them, then actually the whole system of equations is uncommon. So a 4-term arithmetic progression is one of these things. Essentially, right, what are these? These are kind of 4 variable systems that have rank 2, roughly speaking. Okay, so why is this interesting? Well, we think it's nice because, so we've answered this question of Saad and Wolf about this 4-term arithmetic progression, but somehow the fact that this much more general thing is true suggests that actually it wasn't the case that it was some specific geometric structure inside the 4-term arithmetic progression that was causing this to be uncommon, right? Because we've got all these different systems, which essentially the exact same proof shows that it's uncommon. We don't use any particular structure about the 4-term arithmetic progression other than it can be written like this, where these A, B, C, Ds at various points are non-zero. There's nothing special about the fact that our points kind of irregularly spaced or anything. Okay, so maybe I'll briefly give you some details about how the proof goes. So now it's gonna be slightly more technical. Okay. So suppose you've got a function f from fq to the n to r, and we've got a system of equations. Well, right, there's a natural correspondence between sets and characteristic functions. And so in general, in fact, you can get a functional notion of commonness, which is what I'm going to talk about now. And it's actually much more convenient to work with this functional notion of commonness when you want to show that things are uncommon. It's easier to try and construct functions than to try and construct sets. And if you have functions, you can use Fourier tricks and do things with the functions. So let's define this lambda LF. And what is this going to be? Well, it's just, think of it as being the average weight of a solution under F. So what do we do? So for every solution, you take the product of, I guess, the weight of these components of your solution, and then this is just the average. And you can show that there's an equivalent definition of commonness, which says, well, we have, again before, right, we defined we gave a definition of commonness in terms of the number of monochromatic solutions for a sensible system with k variables. Now we're just going to do exactly the same thing, but it's a functional notion. So the definition, which is an equivalent definition, says that the sensible k variable system is common if and only if for every function of this form, the density or the weight of solutions here plus the weight of solutions here is at least 2 to the 1 minus k. So this is the definition we're going to work with. What is the main component to our proof? Well, we prove this theorem, which we sort of call our technical theorem. And what does this theorem say? Well, it says that a sensible system is uncommon if we can find a function that sums to 0, where we're summing over q to the n, such that, and this is, I guess, the interesting thing, when you take the sum of this lambda L prime f over all subsystems that we call critical subsystems, this is negative. So roughly speaking, what does this theorem say? So remember that if we wanted to show a system is common or uncommon, right? We want to show something's uncommon. We want to show something's uncommon. We need to find some function f such that this plus this is less than 2 to the 1 minus k, where an L could be some big, complicated system. What our little theorem tells us here is that if we want to show a system is uncommon, it's enough to find some function and analyze its behavior on these subsystems that we call critical subsystems. Now, why does this help us? Well, the critical subsystems actually always have rank 1 or 2. So this is very nice because this is, instead of now having to think about, if I go again back to this definition, instead of having to understand what this is for a very, complex system, actually this turns the problem into a problem where we just have to construct a function that does something on these fairly simple subsystems. And we know, as we talked about before, that these systems of single equations are very, well understood. So basically our proof proceeds by trying to find some function f that does this, right? So that the sum over our critical subsystems is negative. So I guess the key kind of useful thing is the fact that we can turn the problem into a problem where we just have to construct a function which does certain things with low rank subsystems. And then we have to make this function. But okay, so how do we make this function? Okay, so what we want is we want some function f such that the sum of all these critical subsystems is negative for some f. Okay, so we said that the critical subsystems, we have rank 1 subsystems and we have rank 2 subsystems. Well, actually turns out that it's quite easy to ignore the contribution of these rank 1 systems because this is always going to be small. You can make a function f so that the non-trivial Fourier coefficients of f are small. And there's the way I mentioned before that there was this construction of Gowers that constructed this set with few 4-term arithmetic regressions that was random-like. And I said, what did that mean? It meant that the non-trivial Fourier coefficients were small. So we essentially use the same trick Gowers does to make this happen. So how does this work? Well, we let f be equal to, let's say, g of psi, where psi can be anything we want. And g is essentially multiplying psi by some quadratic phase functions. And by just kind of standard analysis of, you can do a short calculation and basically, right, multiplying your psi by the suitably chosen quadratic phase functions is going to make this small. So there's nothing really clever going on there. The rank 2 systems, right? So we've got L prime critical. So in particular, the 4-term arithmetic progression is a critical subsystem. If we have a system containing a 4-term arithmetic, I realize I haven't defined for you exactly the definition of a critical subsystem. I'm sort of asking you to sort of imagine what they are without telling you what they are, because it's slightly fiddly to define. But right, so there's ones which, so essentially what are, okay, let me tell you what they are. So if you have a system containing a 4-term arithmetic progression, the critical subsystems essentially, for any system, how you find them is you look at what the shortest weight of, or shortest length of an equation that's in the span of your system is. So if you have a 4-term arithmetic progression, we saw that this was a 3 variable equation and another 3 variable equation. And however you take combinations of these, you can't possibly get a 2 variable equation out of them. So the shortest equation here is 3. So the critical subsystems are, essentially speaking, kind of the shortest subsystems that you can make from your big system. Why do they have rank 1 or rank 2? Well, I'm not going to go so much into the proof, but kind of there's a parity issue going on. So if your shortest equation was even, and it was just a single equation, and it had 4 variables, then all your critical subsystems, if they were all even, they would just have rank 1. The issue is if your shortest equation is odd, then actually the critical subsystems also include kind of rank 2 subsystems that contain this odd equation. So we've got feel like my attempt to make critical equations less confusing has made it slightly more confusing. But perhaps just imagine, so imagine we've got a system containing a 4-term arithmetic progression. We've got rank 1 systems, which might be some 3 short single equation systems in 4 variables or 3 variables. And we've got these rank 2 systems, which are systems which have, like the 4-term arithmetic progression, so 4 variables, 2 and 3 variables. So we've got our critical systems, which, let's imagine they just look like 4-term arithmetic progressions. How do we deal with these rank 2 systems? Well, the key thing here, so we've got rid of the rank 1 systems. For the rank 2 systems, you can pick, I said that we've got some function psi, we multiply it by some suitably chosen quadratic phase functions. If you pick this in the right way, you can do it in a way that actually, when you look at all your rank 2 systems, it actually sort of pulls out the density, the weight of solutions for a 4-term arithmetic progression where on this function psi. So we looked at this, we let f be equal to g of psi. The g is very nice because it firstly kills all these the contribution from the rank 1 systems. And it also says, if we look at the rank 2 systems, well, actually, you can pick this in such a way, and I'm waving my hands here, that essentially it pulls out the contribution from the 4-term arithmetic progression. So you pick this g, given the 4-term arithmetic, you pick this g cleverly based on the 4-term arithmetic progression. So now, essentially, what we have to do is it says all you need to do now is come up with a function psi such that the average weight of solutions of your 4-term arithmetic progression given psi is less than some negative constant. And this isn't a trivial step. It was actually quite difficult to come up with this function. So this function by itself shows that a 4-term arithmetic progression is uncommon just on its own, right? If you just look at this kind of if you put it backwards. So there are kind of two main components to the proof. The first one is coming up with this psi that works for this 4-term arithmetic progression, or for any of your little systems that I talked about, right? I said we have this 4-term arithmetic progression theorem, but we also have the more general theorem. We actually have a psi that works simultaneously for all these systems. And then the second step is using this operator, which says actually that this is all we care about and we can get rid of the other subsystems. Okay. So I realize I probably confused some of you there. It's quite hard to give a good idea without writing horrible slides of notation, which might confuse you in a different way. But the key idea really is that we have this nice theorem which says all we need to do is think about these low rank subsystems. And then once we get to that point, how do we do that? Well, we can use some nice techniques or some ideas that actually appeared in Gowers' paper that allow us to kind of pull out what it is we want to do. Okay, so what time do you want me to finish talking?
I think you have still like 10 minutes.
Okay, so I'll not hurry then. Okay, so let me just finish with some closing remarks. So a question that a lot of people ask me when I tell them what we've been thinking about, common and uncommon systems of equations, is whether there's a relationship between what you can do for equations and what you can do in the graph setting. So is it the case that there are specific systems of equations that correspond to specific subgraphs? The answer is pretty much no, there isn't a particularly nice relationship here. Like it would be nice if you could somehow prove some theorems about equations and they would tell you whether certain graphs were common or uncommon. There isn't any broad correspondence. What is nice is that techniques that people use to prove things in the graph setting seem to come across and work for the equation setting. So our second paper where we prove certain systems are Sidorenko, we actually use some ideas from some of the papers that prove that some graphs are Sidorenko. So it's quite nice that the techniques in these areas seem to work for equations and graphs pretty similarly. I don't know of any way that you can kind of prove things about graphs by proving things about equations or the other way around, perhaps for some really, really specific contrived examples, but I don't think there's anything nice broadly going on. So just to summarize, so I've talked a lot about uncommon systems. What about systems that are common? Well, for a single equation, everything is very, very well understood. So I remember I stated this theorem, which said that we've got L of x is this single equation. We know that it's common whenever k is odd. And if k is even, well, it's common if and only if the coefficients can be partitioned into pairs which sum to 0. So there's a really nice characterization of single equation systems. Now, this second part of the theorem, which says if k is even, L is common if and only if the coefficients can be partitioned into pairs that sum to 0. Actually, you can generalize this idea. So if you have a system where over the whole system, your pairs match up. So for example, here, then we can show that this system is common. But again, right, this is a very kind of structured family of systems here. We take several of these equations and the pairs all match up in the same way. It's not, I wouldn't say it's a particularly interesting family necessarily. So you can, doing this, make a large family of common systems. And in fact, the proof gives that they're Sidorenko, but I said we wouldn't talk too much about that. We're talking about commonness. But the theorem that I spent some time talking about actually gives a large family that's not Sidorenko, right? So any system containing a 4-term arithmetic progression, or indeed any system containing something like this, is uncommon. So we've got a lot of common systems, we've got a lot of uncommon systems, but we're actually still very far from having a complete understanding about systems of equations, or even a complete understanding of, for example, systems of pairs of equations. It seems that there's a lot of, it's possible we're not thinking about things in the right way, but we can't even, for example, classify all systems of 2 equations on 5 variables, right? There are kind of tricky things that turn up. So there's a lot of very kind of interesting types of systems to think about. But obviously the nicest thing would be to try and come up with it would be very nice if there was a very nice full classification. Right, the single equation case is so clean and nice, the way that everyone understands what's going on now. For multiple equations, we're very far from that. Just finally, a less broad question. So an equation is translation invariant if the coefficients sum to 0. We think it would be interesting to see, is there a system? So I'm going to sort of add a caveat here. I'm going to say, is there a kind of non-silly, and I'll explain what I mean by that, system of at least 2 equations that is common but not translation invariant. So of course, what you can do, right, remember this, a single equation, you have a 3 variable, any 3 variable single equation is common, and you can put the coefficients for whatever you want. So you could take one single equation on 3 variables with whatever coefficients you like, and then you could take another 3 variable equation on a completely different set of variables and put these together and call them a system. Yes, okay, technically that's a system of at least 2 equations that's common, but somehow your variables, they don't interact at all. So that's not, it's not in really the spirit. The spirit is, can we come up, is there a system that's like not formed by sticking together these single equation common systems? Is there something that's common for, which is with some kind of interaction between all the parts of the system and not translation invariant? And I think I'll stop there, and then you'll have some time to ask questions. But I think there's a lot of really nice different questions in the area. So if you look at both of our papers, they both have kind of conclusion sections. Well, while we were kind of writing things up, and we came up with probably pages and pages of interesting questions about specific things we thought about. And then, so there's a lot of nice things that you could think about if you wanted to. Well, thank you very much. And do you have any questions?
Okay, thank you, Tash. And before turning to the questions bit, I invite everyone to unmute themselves and give a round of applause for Tash's very nice talk. So, any questions to Tash? Jan?
So sorry, Tash, so what is translation invariance?
Oh, the coefficient sum to 0 in a single equation.
Okay, good, thanks.
So yeah, so if you, right, all these systems, if I go, let me go back. All these systems that we can prove that are common essentially are sticking together these Sidorenko equations, right? So every single one, it's just the pairs will match up. We don't have anything that's common that somehow looks more interesting than this.
So I have a question. In this just one equation world, where so the commonness is fully characterized, is commonness the same as Sidorenko, or there is a difference?
It's different. So,
and then is there a characterization of one equation systems that are Sidorenko?
yes. So in fact, if I go, so yeah, no, it's completely understood and it's completely characterized. So there's a you could write this theorem with Sidorenko in here as well. I mean, when I say you could write it, you can. It's completely understood.
Mm-hmm. Thanks.
And similarly, it's not completely understood for multiple systems. So we can say it's essentially Sidorenko whenever the systems, all the pairs match up together.
So if there are no more, let's say, official questions to Tash or recorded questions to Tash, then let's thanks Tash once again for her early morning talk.
It doesn't feel, I've sort of managed to wake up over the course of the talk. So now I'm.
Great. Okay, thank you, Tash.
There's a beautiful sunrise, which you can't see because I've got this background.